Lesson 8.1, Motion Graphs. There are three types of graph shapes you should recognize from your math classes: a flat graph, a linear graph, and a quadratic graph. Each of these three graphs will be applied to our motion graphs today in physics. A flat graph has the equation y equals some number, and it has no slope. A linear graph has the equation y equals mx as long as the graph goes to the origin. This graph has a constant, unchanging slope. A quadratic graph is y is proportional to x squared. This graph has a changing slope, and you can recognize it by the squared in its equation. First, we're going to look at displacement as a function of time graphs and see how these graph shapes change the meaning of the graph. The title, Displacement as a Function of Time, is the full title for these graph types. In the full title, the y variable, or the y quantity, is always listed first. They're written out as y as a function of x. It's a rule of thumb in your labs. The y-axis quantity will always be your responding variable. Your x-axis will always have your manipulated variable on it. As a short form to make saying the title a little faster, sometimes we also will refer to these as d versus t graphs. But again, in this shortened version of the title, the first listed quantity is the y-axis quantity. Let's look at the units of the slope of a d versus t graph. The slope is equal to rise over run, which means it's meters over seconds. Looking at the units of the slope, we can see that the slope is v, because v has the units meters per second. So the slope of a d versus t graph is equal to velocity. Back to our three graph shapes and how they relate to d versus t graphs. A flat graph means d equals some number. This graph has no slope, and because it has no slope and slope is velocity, it has no velocity, which means that the object is not moving if the graph is flat. If it's a linear graph, that means we have an equation like y equals mx, y is d, m is v, and x is t. This is a constant slope graph, which means we have constant velocity. A quadratic graph on a d versus t graph has the equation something like y equals x squared. This looks similar to one of our uniform acceleration equations, like d equals vit plus 1/2 at squared, where you see the t is squared. It has a changing slope, which means we have a changing speed, which means basically the graph is accelerating. So in review, a flat graph means the object is not moving. A linear graph means we have constant speed. And a quadratic curved graph means there's acceleration. Here's an example. If a dt graph has a negative slope, which means it's sloping downward, that means we have negative velocity. Now remember that negatives in velocity don't mean lack of velocity. Negative is a type of direction. This means our direction is backwards, or west, or left, or down, or south. So the object is moving backwards or one of our negative directions. Here's another example with curved graph shapes. If we look at the first two graphs here, we can see in both of them that the d is increasing. The d numbers get bigger as you go along in time. As a result, we know that the speed is forward because it continues to increase the d. In the second two, the d is decreasing. It's getting closer and closer to 0. This means the object is moving backwards, or the speed is backwards. Looking at the first graph only here, we can see that the graph is becoming steeper. If you go along, it's getting closer and closer to being completely vertical. As a result, we know that v is increasing because the slope is increasing. This means that the object is speeding up while moving forward. In the second graph, the graph shape is becoming flatter. You can see that it's becoming flatter because it's becoming closer and closer to a horizontal line. This means that the v is decreasing because the slope is decreasing. This means the object is slowing down. The v is decreasing while moving forward. The second two set of graphs have the velocity in a backwards direction. The first one is becoming more flat. When the graph becomes more flat, we know that the v is decreasing because the slope is decreasing. So in the third d versus t graph, the object is slowing while traveling backwards. And in the final d versus t graph, we can see that the graph is becoming much steeper. It's getting closer to a vertical line. As a graph becomes steeper, we know that the v is increasing because the slope is increasing. This means that it's speeding up while traveling backwards. We are also going to look at a second type of motion graph, the velocity as a function of time graph. In this case, the full title means the same thing as it did in the first type of graph. We can shorten it to call it a v versus t graph. And as before, the first listed quantity is the y-axis quantity and the second goes on the x-axis. We'll start by looking to see what the slope of a v versus t graph means. So if we look at a v versus t graph, the slope is equal to the rise over the run. This is the units meters per second divided by seconds. This is equal to a meter per second squared, which should look pretty familiar to you. A meter per second squared is the unit of acceleration. So the slope of a v versus t graph is the acceleration of the object. We're only going to look at two types of graph shapes for v versus t, the flat graph and the linear graph. The curved graph gets a little bit complicated to interpret, so we're just going to look at these two. First, the flat graph. For a flat graph, that means the y variable v equals some number. It has no slope. This means that it has no acceleration. If there's no acceleration, that means the situation is constant velocity. The second type of graph is the linear graph, which has the equation y equals mx. Since y is v and m is a and x is t, this has the equation v equals at. It has a constant slope, which means it has a constant acceleration because acceleration is slope. flat graph is constant v, a linear graph is constant acceleration. Here's an example of looking at 4 different types of linear graphs for a v versus t. In the first graph, we have positive velocity and positive slope, which means we have positive acceleration. Whenever the sign for v and a match, as in this case, they're both positive, we have an object that's speeding up. Since v is positive, we know it's speeding up in a positive direction. So we would say speeding up while moving forward. In the second example, we have a positive velocity and a negative slope, which means we have negative acceleration. Whenever the signs are different, like positive and negative, we know the object is slowing down. This means that it's slowing down, but since v is positive, it's slowing down while moving forward. Of course, when we say forward, we actually refer to any positive direction. So forward could, in this case, mean north, up, east, or right. In the third graph, we have a negative velocity because it's in a negative quadrant, and a negative slope, which means negative acceleration. In this case, the signs also match, negative and negative, and this means that the object is speeding up. Since v is negative, it's moving in a backwards direction, so it's speeding up in a backwards direction. The final graph has a negative v, but a positive slope, which means a positive acceleration. The signs are opposite, which means we know that the object is slowing down. And since it's a negative v, we know it's slowing down while moving backwards. And of course, backwards could refer to any of our negative directions, which include south, down, west, or left. Here's an example that crosses quadrants on a v versus t graph. In this graph, we have 3 different types of motion happening. It is important to recognize that throughout the whole trip, the object has a constant acceleration, and this is because the slope remains constant. It doesn't change. What does change throughout is the speed. In the first quadrant, we can see that the speed is positive because it's in a positive quadrant. However, the acceleration is negative because it's a negative slope. Positive and negative means slowing down. At the x-intercept, the v is 0, so that means the object is stopped. And in the bottom quadrant, we have negative v and negative a. The signs match, so the object is speeding up. This graph could represent the motion of, for example, a ball traveling up in the air and falling back down again. On the way up, the ball is slowing down. At the top, the ball is stopped. And on the way back down, it speeds up as it falls.